Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over some practice problems where you need to assign formal charges to atoms. And so here are some molecules and some ions. You may have seen these before from another video, but this time these are we're going to add formal charges to our Lewis dot structures. Now again, some of these Lewis dot structures may not be the best Lewis dot structures. In another video, I talk about how to use formal charge to figure out what the best Lewis dot structure is. These aren't wrong Lewis dot structures, but they may not be the best. Okay, but in this video, we're just going to focus on assigning formal charge and getting practice. So we'll start with carbon dioxide. Carbon dioxide has 0 charge, so the formal charges should add up to 0. So, for this oxygen, we're going to use the equation. Formal charge is equal to valence electrons minus non-bonding electrons, these are your lone pairs, minus 1/2 bonding electrons. So, oops, let's call that Ne for non-bonding electrons. So this is our equation. So for this oxygen, since it's in group 6, so you have 6, and I'll do some of the math up here. So here we have 6, and then we have 2 non-bonding, so that's 4 electrons total, minus 4, and we have 2 bonding, 2 bonds, so that's 2 pairs of bonding electrons, so that's 4, but we're going to take half of that, and that's 2. And that works out to the same as 1 electron per bond. So we have 2 bonds, so we're going to subtract out 2 electrons. And that equals, so 6 minus 4 minus 2 equals 0. So this one's going to have 0 formal charge. All right, we could do the same calculation for if you look at the bonding pattern here, the bonding pattern is the bonding pattern of oxygen here fits the common bonding pattern you would expect oxygen to have. 2 bonds, 2 lone pairs, 0 charge. This one has the exact same bonding pattern, 2 bonds, 2 lone pairs, so you would expect it to have the same formal charge, so you don't need to do the calculation. So this one should have 0 formal charge as well. Now what about the carbon? So if we do the calculation up here, so carbon is in group 4, so it has 4 valence electrons. It has no lone pairs, so 0 for the non-bonding electrons. And it has 4 bonds, 1, 2, 3, 4, 1 electron per bond, so that's going to be minus 4. So 4 minus 4 is 0. So the carbon here also has 0 formal charge. And so you could see that the zeros add up to 0, which is no charge on your carbon dioxide. So that's how formal charge works. Okay, what about B, your phosphoric acid? So here we have phosphoric acid. So we could do the hydrogen, right? So hydrogen is in, for example, if we're looking at hydrogen, it's in group 1, so it has 1 valence electron, minus 0 for the non-bonding electrons because there's no lone pairs, and it has 1 bond, so minus 1 because it's 1 electron per bond, and so that adds up to 0. So all of these hydrogens have the same bonding pattern, so they're all going to be 0 formal charge. Okay. What about these 3 oxygens? We'll save that one for later because it's got a different bonding pattern. These 3 all fit the same bonding pattern. So this has 2 bonds, 2 lone pairs, 2 bonds, 2 lone pairs, 2 bonds, 2 lone pairs. So we did the calculation up here for this oxygen, 2 bonds, 2 lone pairs, and it was 0. Since these oxygens fit the same bonding pattern, it's also going to be 0. So, so this is going to be 0, 0, and 0. And that's because, again, with the oxygens, you have 6 valence electrons because it's in group 6. You have 2 non-bonding pair or lone pairs, so that's going to be 4 minus 4. And you've got 2 bonds, 1 electron per bond, so you have minus 2, and that adds to 0. Well, what about this oxygen here? Well, if you know the bonding pattern, if you've memorized it, then you know, well, if oxygen has 1 bond and 3 lone pairs, that ends up having a formal charge of -1. I happen to know that because when you work with Lewis dot structures enough with oxygen, you tend to remember. But if you don't remember, no big deal. Just use the formal charge equation and figure out the formal charge doing that. So for this oxygen, again, oxygen has 6 valence electrons. So you got 6 for that. Notice that oxygen has 3 non-bonding pairs or lone pairs. So that's going to be 6. So we're going to subtract out 6. And then you've got 1 bond. So 1 more electron to subtract out. So 1 per bond. So subtract out that. And this ends up being a -1 formal charge. So you have a -1. Now, one of the things I'll point out again is that the formal charges should add up to whatever the total charge here. It's 0. We still need to do phosphorus here. So phosphorus, if we do phosphorus, right? So phosphorus, we have phosphorus is in group 5, so it should have 5 valence electrons. It has 0 non-bonding electrons, no lone pairs, so that's going to be -0. And it's got 1, 2, 3, 4 bonds, so 4 electrons. We're going to subtract out 4 electrons. So 5 minus 0 minus 4 gives us a +1. So this phosphorus has a +1 charge on it. Okay, so the formal charges here, they're all 0 except for phosphorus and this oxygen, and so that's going to be +1 minus 1, and so that adds up to 0 is what you expect. So that's the formal charges for those. Same thing here. So for if the fluorine, we have fluorine. So for fluorine is in group 7. So that's 7 valence electrons. And you've got 3 non-bonding pairs, 3 lone pairs. So that's 6 electrons. So we're going to subtract 6 for those. And then it's got 1 bond. So that's 1 more electron to subtract. So we're going to subtract out that one. And we got 0 formal charge. And so remember the bonding pair, if you remember the bonding pair of halogens, or the bonding pattern of halogens, especially fluorine loves to only have 1 bond and 3 lone pairs. So this fits the bonding pattern, and you'll notice that it's also formal charge. So if you fit the bonding pattern, you're most likely to have 0 charge. Okay, so since these fluorines fit the same bonding pattern, so that 0 is going to apply to both. So we have 0 formal charge, 0 formal charge there. What about the oxygen? What we said before about the oxygen with 1 bond and 3 lone pairs, it's going to have a -1. So we put a -1 formal charge. And then we finally have the selenium. Selenium is in group 6. So we'll put Se, selenium. So it's in group 6, so it has 6 valence electrons. It has one lone pair, so we're going to subtract out 2 for the lone pair. And it's got 1, 2, 3 bonds, so 1 electron for each bond, so we're going to subtract out 3, and that's going to be a +1. So we have a +1 formal charge there. Notice that this is neutral, and notice that the formal charges cancel each other out, so this is neutral. Okay, good job. So what about this one here? This is your SO3 2 minus molecule. Again, you might notice that this is maybe from other places you've seen this written differently. That's because we haven't talked about resonance structure or anything like that, or trying to figure out the best Lewis dot structure. But this is a legitimate Lewis dot structure. It obeys all the steps. So right now we're just focused on assigning formal charge. We'll use formal charge later to figure out what's the best Lewis dot structure. So here again we have oxygens with 1 bond and 3 lone pairs. So that fits the pattern up here. We said that was -1 because that's what we calculated it to be. Okay, so we calculated it to be -1. 6 valence electrons minus 6 lone pairs, minus 6 electrons from the lone pairs, -1 for the bond gives you -1. So same bonding pattern, same formal charge. And then what about sulfur? Well, sulfur is in group 6 too. So if we do if we do sulfur up here, so we have group 6 element has 6 valence electrons. We have 1 lone pair, so we're going to subtract out 2 electrons for the lone pair, and we got 1, 2, 3 bonds. So we're going to subtract out 3 electrons, 1 from each bond, and that gives us a +1 formal charge. So the sulfur has a +1 formal charge. Now if you add up all the formal charges, it's -1, -1, -1, +1. These two might cancel out, so those two will cancel out. We have these two left, so we have a -2. So that we got the 2 negative charge on our SO3 2 minus. Okay, what about the next one? Again, 1 bond, 3 lone pairs. That's going to be a -1. 2 bonds, 2 lone pairs. That fits the bonding pattern, so that's going to be 0. What about the nitrogen? Nitrogen is in group 5. So that's going to have 5 valence electrons. It's got 1 lone pair, so we'll subtract out 2 electrons for the lone pair, and we got 1, 2, 3 bonds. So 1 electron from each bond, so that's 3, and we get 0. So also, it fits the bonding pattern. Nitrogen wants 3 bonds and 1 lone pair. So it makes sense that it's going to have 0 formal charge. And last, we have our molecule here, the P2H4. Again, hydrogen only wants 1 bond, so that fits the bonding pattern from hydrogen. And we saw here that there's 0, so it's going to be 0 again. Same bonding pattern, same formal charge. 0, 0. Now what about phosphorus? So phosphorus here has 3 bonds. Notice that phosphorus is in the same group as nitrogen. So if nitrogen has a particular bonding pattern that it tends to follow, and phosphorus is in the same group, you would expect phosphorus to follow the same bonding pattern because elements in the same group tend to have the same properties. So if you have phosphorus, so it's in group 5, so 5 electrons minus 1 lone pair, so that's going to be 2 electrons for the lone pair, and then we have 3 bonds minus 3 for 3 bonds, and then that gives us 0. So each of these is 0 because they have the same bonding pattern, and they have the same bonding pattern as nitrogen. So that's also something you want to pay attention to as well. If you enjoyed this video, if this was helpful, like the video, subscribe, make a comment in the comment section. I'll see you next time.